All right, here's a few news articles. This one's interesting. The zero logon vulnerability has been hitting the news a lot lately. And what this does is it lets you escalate to domain administrator on a Microsoft domain without a password. You have to have access to the domain controller, but then you can escalate to domain administrator. So what these guys found was they could send a phishing email, and when somebody clicks on it and they get access to one machine, they could then take over the whole enterprise and encrypt it all in just 5 hours. So that's pretty impressive, and it's worth seeing what they did here. They moved laterally. So now after they reset the machine password of the primary domain controller, then they moved using PowerShell, Active Directory, and Net, and then they used Cobalt Strike. And this is why, again, there's a lot of people getting angry, saying that they shouldn't make all these hacking tools like the kind we use in the penetration testing class, which can then be used by real criminals. So it is an interesting, constant ethical struggle. There are some people that say you should not be publishing vulnerabilities, proof of concept code, pen testing tools. It's legal to do it in America, and people do, and France and a lot of other countries. But increasingly, these pen testing tools are being used by real criminals, and that does concern some people. So Trump took this special antibody treatment, which was experimental and not even approved yet, but he got a special exception. And as you saw, he recovered quite quickly from coronavirus. And they say this stuff is actually very good. They took a trial here. You have to give it to people when they first test positive, before they're very sick. And then the people that don't get the treatment, 6% of them have to go to the hospital, but the people that get the treatment, only 1% of them have to go to the hospital. So they're still doing trials, but if that's confirmed, that makes this a very effective treatment. But I've read somewhere it's very expensive and the supply is very limited. So it's not clear at all how many people are going to be able to get it. And the worst problem is, of course, since you have to take it early, you have to have enough tests, and we still don't have enough tests, which is kind of mind-boggling. It's been more than 6 months and we still don't have enough tests to test people. So the complete lack of government entirely, where they just don't bother to do anything to prepare for it, is holding us back. Anyway, so that's why it's good for us all to get used to using Zoom and being remote, because I think this will obviously be going on for at least another year and maybe longer than that, because America doesn't seem to have any capability to actually respond in any effective way anytime soon. But that's the first drug I heard that did any good. The other stuff, remdesivir, did no good. That stuff Trump wanted a while ago, the quinine stuff, hydroxyquinone, that didn't do any good. But this antibody stuff apparently actually works. So that's somewhat comforting if they can find some way to manufacture and distribute enough of it. So this is all over the news. These Russian hackers are a Russian gang. They're the GRU, the successors to the KGB, and they've done a whole bunch of political hacks, and they're still doing them. And they attacked a lot of American databases, and they've now been indicted, and they have published pictures of them, which, of course, the United States has been doing for a while to Chinese and Russian hackers. Now, we probably can't really arrest them, but it's sort of a public relations move. These are the guys that hacked the Olympics in Tokyo and many other places. And they are certainly attacking the United States. They disrupted the presidential election in France by trying to mess with Macron on leaks. The Russians seem to do the same thing over and over again. In 2016, after Trump asked them to do it publicly, they hacked the Democratic National Convention and dumped out Hillary's emails. And they've done the same thing over and over and over exactly. They did it to Macron. They just tried to do it to Hunter Biden. They get some emails, and then reportedly they mix forged emails in with the real emails and then release it. And that's what they've done many times in the past, and that's what people suspect they are doing now with Hunter Biden. But anyway, there's a very good article here from Nicole Pearl-Roth, who's a very good New York Times reporter and came and visited us, and explains what's happening here. The United States knows we are under attack to influence our election from Russia, and the problem is that the president will not do anything about it. He's totally on board with Russia, and he won't let anybody talk about Russia hacking us. He's convinced it's all fake, and any talk about that is an attack on him. So our The FBI director is clearly trying to do something about it. I think he must have resigned to the fact that he's going to get fired after the election. Ray has been speaking up, and you don't speak up about Russia around Trump unless you want to get fired. And now companies in America like Microsoft are trying to protect our nation from the Russians. Since our president will do nothing and our law enforcement can't do much, it's up to individual companies to fight off the Russian network. So Microsoft took down 90% of the botnet that Russia uses to perform the crypto blocker part of this attack. And what they're hoping to do is to somehow hold back Russia by harassing them and slowing them down. It's very unclear that these steps will work, but it is necessary to do something, or you can just let them hack our nation and install leaders that are not really of our choice, like they did in 2016. So anyway, it's interesting to see, like so many other issues these days, the truth about it is out there, and it is extremely obvious that a large portion of Americans will just never see this and never believe it because they only watch government propaganda instead of actual news. So anyway, it's interesting to read. It's interesting politically and technically. As you see how it's going along. Twitter got hacked a while ago. A lot of famous people got hacked, and they found out how they did it. They found Twitter's VPN software, and they put up a fake VPN login page with a URL that was close to the right URL, but not exactly right. And then they just used social engineering, the #1 most effective technique. They called up people. A 17-year-old attacker would call up these people and say, we're your IT network, we're testing this new VPN login, please go here and see if it works. And they would then log in. And even if they had two-factor authentication, they would log into the fake page at two-factor authentication, which the hackers would then type into the real page and get in. This is extremely effective and very hard to stop. So we'll see what happens. Although one thing that I think would help, of course, is if you had a record of only what IP addresses are allowed in, but then people wouldn't be able to log in while they're traveling, and that's the whole point. So, anyway, it's basically social engineering that got them in, and social engineering is famously very difficult to stop. So Facebook has begun banning political posts, like Twitter has, and this is very surprising because Mark Zuckerberg was a very close ally with Trump and very much coddling the Republicans, and they're the main tool used by Republicans to push voter suppression and false news to people. And they were right on board with that and selling them that ability. And people wondered if Facebook has finally changed their mind here, because the more cynical people have said they're just doing it because Trump might lose, and then they don't want revenge from Biden. But anyway, what Mark Zuckerberg just announced in his meeting is that Facebook is just doing this temporarily because of the election, and after the election, they plan to just open up and let people post any kind of lies they want again. So it's not clear, but I mean, one thing that's certainly come up many times, he thinks he's Augustus. He models himself after Augustus Caesar and hits his haircut. I think he wants to be president. That's his plan. But he hasn't yet run for president officially. I don't know why, but I think that's coming quite soon. But I think everyone who's kind of on the right like this is just hiding until after the election, because there's likely to be a disaster for the Republicans and a shakeup and a whole reforming of the party. And so it's probably the wrong time to step up as a leader. Anyway, so these guys use Zoom, and they're doing exactly the technique that when you're doing in the projects in this class, they're using DIL hijacking to take over Zoom. So they put a DIL on your machine, which has the same name as a DIL used by Zoom, and Zoom apparently has the same vulnerability as several products we were talking about last time, where it hunts for the library to load it. So if you put it somewhere earlier in this series, it will find the fake DIL. They've got a DIL that's good enough to fool Zoom, probably by using the technique we did last time, where you make a DIL forwarder, and they and that's how they got in. So that's pretty good thing, fun. cmmlive.dil. I see a question. What's the website link on antibody vaccination? Well, all these are on my news page. So if you go to samsclass.info, then click news, and you'll find them all here. All right. Anyway, so I'm glad to see it. That's DIL injection is what people are really using. And I go to right on time. I'm just amazed here. They've got a list of the American response to COVID, and it is just unbelievable. Almost all of the country is in a state of uncontrolled spread. I just heard today Europe is moving up really fast, so fast that they expect they'll be having more cases per day than the United States soon, or more likely, the United States will catch up. All along, the United States has been 2 weeks behind Europe. So we're expecting a huge surge in the fall. This would be, if it's like the 1917 or 18 pandemic, I think it was 18, it will have its largest surge in the winter, dwarfing all the rest. So we will have very large amount of cases here, and obviously at least half of Americans will refuse to wear masks and do absolutely nothing and just pretend it's not happening, which will just make it spread farther and faster. So anyway, all right, we're up to here. And I've got quite a lot to show you tonight. I've got 4 new projects, which I'll demonstrate at the end, which is very interesting. I'm very glad a bunch of new things are working, and it's all about kernel debugging. So we're going to talk about kernel debugging and do the theory, and then I'll have a break, and then I'll record a discussion of the 4 new projects where you get to try these things. A lot of new things are working. I'm very pleased with them. So here we are, kernel debugging. And all right. So we're going to talk about, of course, you have to use WinDbg. Now, Debug is very easy to use and very nice for normal user land debugging, normal programs that you launch that run under your user account. But for kernel debugging, you must use WinDbg. As far as I know, there's nothing else that works. So the kernel is very different than user land. Now, in the kernel, you have device drivers. You do not have DIL files. You have drivers, and drivers respond in memory. They load into memory, and then they respond to requests. So they're sort of like services that run in the background. But applications do not directly access kernel drivers. You go through a series of steps. They access what Microsoft calls device objects. And I mentioned before, the way to understand Microsoft names is that every Microsoft name is the opposite of what it is. So a device object is not a physical object. It is a software object representing a hardware device. So that's what a device is in Microsoft world. It's a software representation. So when you add a printer, Microsoft terms, you're adding a device to your machine when you put a printer in the little printer's menu. So the driver creates and destroys devices, which can be accessed from user space. You load the driver creates a software device. So when you plug in a flash drive, Windows creates the device, the object called F. And now applications can read and write to the F drive. So driver loads in the kernel, and that creates a device in user land, and that's what you connect to. If you plug in a second flash drive that's from the same brand, it might use the same driver, and then the same driver will be used to make a second device in user land with a different name. I sent you a link via my iPad. All right, I don't know what that is. Anyway, all right, I'll probably send to the other student. Anyway, so when you load DILs, if you run a process like, Internet Explorer or Microsoft Word or something, it then launches DILs, and the DILs load into memory and export the functions. And then when the library is first loaded, it calls DIL main, which prepares it. And then you can call all the other functions there. All right. So drivers have to be loaded in the kernel. Now, they don't have DILs and DIL main. Instead, they have drivers and driver entry, which is the analogous thing. When a driver first loads, it runs the code at driver entry to prepare the callback object so it's ready to be used. All right, so here you define a callback object, and there's some of the details here about how it's done. Notice these Windows API calls: initialize object attributes, eggs create callback. We're going to see a lot more API calls later, and you just get used to the way they look. This is Microsoft convention where you have capitalize every word, ram them together. You often have extension at one end or the other, and so on. So DILs load in memory when a process is launched, and execute DIL main for the export table. Drivers load into the kernel when the hardware is added. Then they execute driver entry, and then they have callback functions and callback objects. Those are the analogous things. So there's not an export table, it's the callback functions. All right, so here's a normal read request. Your user application gets a file handle to the device. It calls read file, and then the kernel processes the read file request. For malicious requests, you might bypass that. As we mentioned before, you could use the native API where you bypass the convenient features and jump in directly. So it might go directly to device IO control, which will then pass in a buffer of data. And so here's the normal setup. You have a program and exe up here. It normally would go to kernel32.dil, which, remember, the Microsoft convention always works. Kernel32 is called kernel because it is not the kernel. It is a userland object that is a couple steps away from the kernel. Then it calls ntdil, which is the library, which lets you go to NTOS kernel. This is the kernel, NTOS kernel. And then this now calls drivers that are loaded in the kernel, and they contact data structures to get the information, and those eventually go to the hardware. So that's how your calls generally go. So malware might have no user mode component. It might load a driver that is never used to create any object up here because it's not actually intended to serve any userland program. It's just something like a rootkit living in the kernel. Another suspicious activity you might notice. All right, so NTOS kernel and hal.dil are kernel mode objects. Hal.dil is the hardware abstraction layer, and this is used to interact with the main hardware components. It's an essential part of the operating system, but NTOS kernel is the kernel. And all right, those are places you'll have malware connect if they want to go directly to the kernel. So let's take a look at the first cahoots here. And that is one, let's see, favorites. This is 126, there we are, 10A. All right, good. Start this thing. And I'll get ready to record the names here. Good, there we go. Give it a few more seconds. All right. All right. I'll give it 5 more. I guess that's it. All right. What does the application interact with? Okay, it interacts with a device object. It can't interact with the driver because the driver is not in userland. All right. Which code loads into a process? The libraries, the DILs, all right. When a driver is loaded, what procedure is called? Driver entry, good. All right, which one of these runs in user mode? Kernel is the one that runs in user mode. I think HAL doesn't, although I'm not surprised if it's a DIL in kernel. I'm a little confused about that. But anyway, kernel 32 definitely runs in user mode. All right. Kernel, I have to tell you who they are. The third one, I know who that is. The other people will have to tell me if they want to get their points. And it reminds me of my chat message. Chat window has somehow vanished. Chat. Oh, there it is. All right, good. All right. And that's, I know who Kernel is now. All right. All right. And why kernel 32.dil not main kernel? Yes, well, that's a good question. You have to ask Microsoft. But kernel 32 is the library used to get to the kernel. The kernel is NTOS kernel. All right. So if you want to set up kernel debugging, you have to use WinDbg. And if you're going to use a virtual machine, then this used to be very difficult. I'm very glad to say it finally made it easy enough with Windows 10, and we're going to do it later. But it used to be that you had to have a serial port. And this was really quite painful, and my students really didn't like it. Now, in the book, they talk about editing boot.ini, which is what we used back in the days of Windows XP. But now we use bcdedit. There's a binary configuration database for boot up. And so you use bcdedit debug on, and that's what we're going to use in the projects. So you install WinDbg, and you can get the old version if you're using Windows Server 2016, which is in the older projects. And in the new projects, we're using the new version of WinDbg that a student in this class told me about, WinDbg Preview, which is much prettier. But once you get WinDbg, then you can debug on one machine by using livekd, a sysinternals tool. This seems to be built into Windows 10 now with the new version. But you can now debug on one machine. And so here's the projects where we did this debugging on a 2016 server and a 2008 server. So those are available. And so you connect here, and you can then observe the kernel on one machine. You cannot put breakpoints and stop the kernel because that would stop the machine you're using, but you can at least look at the kernel. And so you need to learn some WinDbg command line commands. They're trying to make WinDbg a little friendlier and more graphical like OllyDbg, but it still is largely not. And you pretty much have to learn some command line commands to use it. So D will let you display memory. You can display it as ASCII, as Unicode, or as double bit words, or you can use DB to show it in both hex and as ASCII like you would in a memory dump. Those are all pretty good. So you can display any memory. This will show it as ASCII. You can edit memory, although not if you're doing single machine debugging, of course, but if you have two machines connected, which we're going to talk about later, you can edit the contents of memory with eMemory. So you can write into memory. And you've got mathematical operations, of course, so you can do this. You can show the first argument for a function as a wide character string. This will show it to you that way. You can use ESP+4 to point for things. This is a 32-bit command. In a 64-bit, it would be RSP for the stack pointer in 64-bit. So you can set breakpoints with a normal breakpoint, and then you can express the address any variety of ways. If you have Windows symbols, you can give it the name of an address. So this will breakpoint at the start of this address, and then it will execute what's in quotes here. So when it gets there, it'll break. It'll then execute these debugger commands. This will dump out an object in ASCII, and this will then run again. And we're going to use this structure in the projects later to make a debugger that automatically shows you all the files that are being opened in the kernel, which is very nice. All right, but you can't do any of that breakpoint stuff with livekd debugging on a single machine. All right. But you can list the modules, and we did this before. LM lists your modules, so you see the loaded modules in the current process, and you can also point to other modules and see, like here, this shows you the disk driver. And you can show the start of the module. You can use L to show how many words to show. And this will show you the first 10 words of the module NT. So here you go, DDNT gives you some default number of words. This gives you 10 32-bit words, I think. Looks like it's more than 10. I guess that's, oh, the hexadecimal. That's 16. So these are 4 in a line and 4 lines. All right. .hh gives you help and takes you to this chum file all the way from Windows 95. The CHM is the system they use to make the help files for this, and it's still, that's where the most useful help is. And you can use R to dump out the registers, and there are many online tutorials with a lot of these commands, but I'll show you a few of them in the projects. So let's take a look at another Kahoot. 10B and 126. There it is. All right. All right. I think that's probably as many as we're going to get. I'll give it 5 more seconds. Oh, okay. I'm going to wait a little bit. All right. All right. To set a breakpoint. BP, like you might imagine. Good. Which one shows memory as ASCII? All right, display in ASCII. All right, which one shows kernel drivers? LM shows you loaded modules, including drivers. All right, which one will change memory contents? E commands, edit memory. All right, good. All right. Suarez. All right. So, good. All right, so now we got Microsoft symbols. If you compile code, you typically remove symbols, but Microsoft has published the symbols for the kernel for convenience of debugging, and they made it publicly available, which is pretty nice of them. So if you have symbols, then you can use the API call names and other labels for objects, constants, and routines, instead of having to find the address on your system and refer to it as a numerical address. So you can refer to a module name and then a bang and then the symbol name, or just a module name, and that'll put you at the start of it, or symbols. And so NTOS kernel is the only one I know that doesn't use the full name. This is abbreviated as NT. So you can use NT bang, NT create process, and that will refer to the first address of that function. So we did this before. You can unassemble NT create process, and then it will show you some default number of it, or you can specify how many bytes of it to process here. And it now shows you the beginning of the assembly code unassembled for that process. You can make deferred breakpoints, which will put a breakpoint on this as soon as that module gets loaded, if it's not already loaded. There's a function to find the entry point of a module available if you want to do that. And you can search, which we've done before. This is how you search through the kernel for things. You can use stars, just like you would for file names. So this will look for any function in the kernel, NTOS kernel, that contains the word create process. And as you see, there's a bunch of them, NT, ZW, and so on. All right. So you can also list the closest symbol if you want to. So if you're at an address, it will then move forward until it finds the first named symbol. And that might be useful if you're somehow in the middle of something and you don't know where you are. You can, now there are data structures. This is all in C++ with data structure options. So you have these objects which contain a series of data elements, and you can view them by their symbol names. And then you can even print out the contents of an address in the structure of that known module. So if you have your example here, you can just see what a driver object is, and it has these data fields. So someplace in here is, here's the driver name as a Unicode string, and here's all these other objects. And then you could view a memory location in the format of a driver object, and it would populate it like this to make it easier to understand instead of just giving you a raw hexadecimal output. So there's driver objects and there's device objects. Device objects look like this also. You see the data structures. All right, and so here is overlaying data onto a structure. So in the format of a driver object, I want to see the data at this location. So now it gives me the format here and it fills in the data there. So now I can see the driver name, and here I see the actual string /driver /beep. This is the beep driver, which used to be what happens when you hit Control-G. It goes beep on an old MS-DOS machine. I'm not quite sure what use it is in modern Windows, but the module is still there. All right. And so driver init is called when a driver is loaded, like we said, and you can see it here. Driver init is someplace, yeah, down here is driver init. You can see the address of it here. That's where it's going to go. There's in the structure of the driver is a pointer to the driver init function. All right, and just like when you make a malicious DIL, like we did before with Metasploit, it just puts all the malicious properties inside the DIL main. A malicious driver might well put all the malicious activity in driver init. So it doesn't actually have to make something else call it. It just has to load it, and that'll run the malicious function right away. All right, so there's quite a lot in all the tutorials about WinDbg about how to get the symbols, the Microsoft symbols, without which it's much harder to debug. And they always tell you to execute a bunch of commands to get it and download it. And I'm very pleased to tell you in the latest version of the Windows debug, this just happens automatically, finally. The debug preview just loads symbols. It's very nice. You don't have to configure these ridiculous paths, which you had to do by hand for many years for some reason. You could download the symbols locally in case you had a slow internet connection or you wanted to work on a machine with no internet connection. You could download the symbols and store them locally. But most people just stay connected to the internet and they download them as needed. You do have to get exactly the right symbol set for exactly the version of Windows with the versions of patches you have. So it's not at all simple that you get one version and have to use it all the time. You have to match it exactly to your operating system. This is also a problem for the forensic tool, Memorize, that uses, I think it's Memorize, a very popular forensic tool. The problem is you can take a memory dump from Windows machine and you can analyze it, but then you have to have a data structure that has how to parse it for your version of Windows. And I used to use that tool a lot. The problem is it only had out-of-date versions of Windows available to parse the data. So it is a problem. And at least Microsoft for kernel debugging does provide us a good set of symbols for every version of the operating system, which is very nice. And in a way, it amounts to almost being open source in that they really don't have any secrets. There are undocumented features in the kernel, and you can just figure it out with WinDbg, so nothing can really be undocumented for long. Anyway, you don't have the source code, but you have something close enough to the source code that you can figure out a lot about how Windows works. And of course, the source code's been leaking out. There was a big dump of it last week. All right, I see Nick. Nick has a different name, okay? But I still don't know who Crazy Pigeon is. All right. Anyway, good. All right, I think we had 16 or 17 last time. I'll give it a few more seconds. All right. All right, how do you, oh, sets a breakpoint? How thought we'd done this. Oh, I see a different one. Okay, fair enough. Yeah, that sets a deferred breakpoint at the start of this routine, the entry point of that routine. So it's another way to set a breakpoint. All right. And the type information for structure. Yeah, that's the layout of a structure, those underscores and caps. All right. All the functions in NTOS kernel. Okay, that's this one here, XNT star. We did it last time. All right. All right. All right. Good. All right, so I got a little bit more of this, and then we'll move into the new project. So in practice, if we'll take a look at how this is done. So if you write to a file from user space, like you're using something like Microsoft, from user space, you do something in Microsoft Word and write to a file. But if you try to write to a file from kernel space, that is not a normal thing to do. If you're in the kernel mode, you cannot call user mode functions. So you must use the kernel analogs of these, ntcreate file and ntwrite file. So here's how user space code like a normal product like Microsoft Word would work. Yeah, it just creates a service to load a kernel driver. Let's take, yeah, this is the one. Okay, there's normal user space. So this creates a service with create service. And then you have user space code here. I think this might all be the way malware does. Anyway, the point is, then you just take a look at the names of the function calls here. You create a service, okay, and then you create a file. This gives you a handle to a device object, which is now file writer device. And when you created a file, someplace in here went the file name. Yeah, LP file name is there. And then there is, this is all malware, pardon me. Then you have device IO control to send data to it with device IO control. So you fill a buffer with data and pass it in. You've given it a file name and you've gone through a service to do it. So you had to go through a few steps to get back to user land and back in. So anyway, you can see kernel modules load if you put it in verbose mode. I haven't tried this yet in the projects. That might be fun. You see it loading modules as it goes along. And if you use VMware, you'll see this one thing loading and unloading all the time. That is part of VMware and not a malicious activity. All right. So drive object, we'll show you a driver object in kernel mode so you can see this particular loaded driver. And it'll show you its object, loading its symbols, show you where it is. And DT will show you a structure of an object, and so it'll load the data at that memory and present it as a driver object like we said before. And when you have file names, you see it uses this fully qualified object name, which is more complicated than a file name. If you remember the old days of Windows XP, you would see this stuff in boot.ini. This is how you actually refer to hardware from the root. There's a fundamental problem with Windows is it uses these drive letters, and if you play with Windows tech support, you'll notice something horrible. If you define a drive called C and D, and then you change something and reboot the machine, those letters will change. Those letters are not actually written anywhere on the drive. They are assigned in boot up in order. These are not really specifiers of it, so you have to have other things here that will actually give you a fully qualified object name to point to something. Anyway, so applications work with devices, not drivers, as we said, the devices being the user land software objects that are used to move data to devices. So you use dev object to find out about a device object and dev handles to find the handles in user mode. So rootkits modify the internal functionality of the operating system to conceal themselves. There are user mode rootkits, which are weaker, and there are kernel mode rootkits, which are the strongest. Now, the old-fashioned way rootkits worked up until maybe around Windows Vista or so was by hooking the SSDT. And so if you do the old projects on Windows 2008, you actually install some stuff and see it modify the SSDT. I don't think we can do that anymore on Windows 10, and I don't currently have a kernel rootkit project for Windows 10. I'd like to add one, but I'm still working on finding one we can use. But the SSDT is a place to hook in, and this is how security products used to work. And one of the things I used in there was the zone alarm firewall. The old firewalls used to hook in here. So what's going on here is the SSDT is a table which looks up function calls in the kernel. And this is where you go if you use syscall or int2e or sysenter, which you'll see if you're doing the assembly language projects. You jump into the SSDT. The SSDT is a table of pointers that points to kernel mode routines that you can run. So you enter with sysenter, it looks in the EAX register to find out which one you're doing on 32-bit machines, and then it jumps to some location running a kernel module for you. So you put 25 in here, that's ngcreate file, then you put in here a pointer to the file name, and then you execute this sysenter after you set it up, and sysenter will then enter the kernel and use the EAX to tell it which module you're doing, and it will go by means of this lookup table, the SSDT. The SSDT is just a series of addresses that point to all the kernel functions. So if you want to alter the behavior of Windows, you could just, if you wanted to make it create files, and you wanted to change this function, you would just change this address to point to some other code you had added, and then that different function would happen every time anything tried to create a file. So that's the game here. You can hook it. So the rootkit will do what those dill functions we made last time are. It will connect to the real function and do a malicious thing, but most of the time just go to the real function. That means your computer will continue to work normally for most activities, but certain activities it won't act normally. And typically what a rootkit does is it hides things from the operating system. So it has a directory full of files that you can't see. When you do a directory, you can't see them. When your antivirus tries to scan the hard drive, it can't find those files. It has processes running that you can't see. They're not in Task Manager, and so on. That's by hooking these functions, it just hides some part of the operating system from all the other applications running and system files running on there. So you can just look at the SSDT. This is not subtle at all. NTU for example, in this one in the old project, NTUS kernel will load. The kernel is not very big. So all the kernel addresses go from 804 to 806. That's the real kernel. And so if you look at the SSDT, which you can do with this long command, KI service table and all this jazz, you see all these addresses. And you see they're all, this is where the pointer is. This just counts up by 4s, 70, 74, 78. And here's all the addresses pointing to all these NT functions. And so they all start with 82 because they're all pointing to real kernel processes. But if you look at them all, here's an example from the book. In this case, the kernel loaded at 80. And here's a function that's totally not 80. So that's obviously the hook. This one's modified, pointing to some other code. And so it is pretty obvious, easy enough to detect. All right. And so here's a listing of rootkit hook functions. Here's another, some code that finds them. And the hooks are pretty easy. This was a common thing for legitimate software to do, and Microsoft got pretty mad about it because it messed up the operating system, and they made this more difficult. And I don't think you can use this kind of hooks in modern versions of Windows anymore. Rootkits have gotten more complicated. Anyway, now another topic is interrupts. I talked about before. Interrupts are like emergency signals in the operating system that require some handling right away. And there's a whole series of them in the interrupt descriptor table, which you can see with bang IDT. You'll see all these interrupts for things that might happen, something about the clock, something about a broadcast call, something about the serial port. All these things can send signals, like the signal, for example, to shut down your machine. And all right, you can see them there. There is a tool to load a driver. And so I'm going to look into this. I might be able to use this tool or whatever the update of this tool is to load a driver into 64-bit Windows. There is a Microsoft training project where you write your own driver and put it in the kernel of Windows and debug it. And I was planning to give you that, but I didn't get that far. But I may have that project up next week or in a couple of weeks. We'll see how it goes. Anyway, in modern versions of Windows, after Windows XP, which all modern supported versions of Windows are, it's BCD edit instead of boot.ini. And now it has patch guard, which prevents third-party code from modifying the kernel, which is why I don't think we're going to see SSDT hooking anymore. In fact, you can't even run a driver anymore unless it is signed with a real commercial digital signature, although you can boot the machine with this no integrity checks option, and then during that time after that boot, it will accept unsigned drivers, and that's what we'll have to do for a project. So I'm working on that. Anyway, let's take a look at the last cahoots, and then we'll take a break. 10D. All right, I'll give it a few more seconds. All right. So what module is loaded and unloaded by virtual machines? All right, that's K-Mixer. All right, what's the normal function used to execute kernel code? It's now sysenter. These are older ones, syscall int2e. Sysenter is now the one Microsoft uses. All right, what do rootkits modify? The SSDT was the traditional way to make a rootkit until Microsoft enforced had new security features. All right. All right, which one is not in Windows 10? Root.ini, remember that? That's no longer in any version of supported Windows. All right, and if you want to use unsigned device drivers in modern Windows, what do you use? All right, that's it. No integrity checks. We'll be using that in the projects. All right, so I got somebody named S. Nick, I know who that is. And K, I have an idea. I know who that is too. All right. So let's take a 10-minute break. I'll come back at 7. I'm going to stop the recording and process it, and then I'll demonstrate or at least talk about the new projects, which are quite exciting. So let me stop this recording.